Okay, great, thank you. So to start off, I'm going to be showing these slides that John Shimonek presented at MS&T. They're largely from his presentation at MS&T this past year. So this is a joint effort with John Shimonek, Shipin Chin, Shuling Sheng, Zikui Liu, and myself. So integrated first principles calculation and crystal plasticity finite element modeling approach. So I want to talk a little bit about how we're trying to merge these two different modeling approaches to understand the mechanical behavior of materials, which we hope to do in this project as well. But before I do that, I wanted to give just kind of a brief overview of one big slide showing some of the different areas that we're working on in my group. So we're interested in multi-scale mechanical behavior of materials. And in particular, what we aim to do is uncover links among the microstructural features. So by this, we mean phases, grains, grain size, grain morphology, texture, and defects. And then to the multi-axial macroscopic plasticity and fracture behavior. So we want to understand how materials deform and eventually fail. And we do this with combined experiments and computational modeling at different length scales. And so this has many applications. So one of the big focuses in our group right now is on additive manufacturing, but this also has application toward lightweighting of materials, prediction of properties, and then materials design. And so these are some of the areas that we work in. So for additive manufacturing, we're heavily focused on trying to identify processing structure property relationships. And this is some of the recent work that we're doing in terms of using in situ processing signals during additive manufacturing. So this is during a powder bed fusion build, using computer vision technologies to try to then link that those signals to the microstructure and the mechanical properties, with the idea being that then you could monitor your process and have some control where you identify that you've formed a defect and you can fix that during processing by adjusting parameters. We work largely on multi-axial mechanics. So we have this custom built, custom designed test frame where it's about 10 feet tall and it has a vertical actuator and a horizontal actuator. And this allows us to subject materials to any combination of tension and shear loading, which means that we can measure the deformation and failure behavior of a material under complex realistic stress states. So this image is just to kind of represent that lets us get information on plasticity, and that also lets us get information on fracture. And the idea is that we use those experiments to develop and calibrate plasticity and fracture models so that we can then predict and prevent failure in actual components. Some other techniques that we use in situ methods to understand grain level mechanics. So in situ neutron diffraction this is an image of the Vulcan beam line at Oak Ridge National Lab, where we can perform mechanical tests while also measuring neutron diffraction patterns to understand how different grains or phases deform under different environments. And then also this is a small scale mechanical test frame, also custom built, that can be used to interface with optical microscope or scanning electron microscope so we can start to identify grain level behavior. We can then interrogate that further with our computational micromechanics approaches. So this shows, so we do continuum finite element modeling. We also do representative volume element type modeling, which is pictured here, where we can model phases of a material differently and do experiments in the computer and then link those to the actual physical experiments that we perform to understand where damage and deformation localized within microstructures between phases and so forth. And then I'm going to talk today about crystal plasticity finite element modeling as well. And that's what I'll talk about today. And then some of the areas that we're also interested in terms of additive manufacturing are shown here, just sort of for completeness. So functionally graded materials, where we use directed energy deposition additive manufacturing, where you spray the powder into the melt pool to build up your component. And by varying the composition of what we deposit locally, we can then have gradients in composition and therefore gradients in phases and therefore gradients in properties. So this is work that we've done with Zikui Liu over the past few years. And then finally, we're working on lattice structures as well. So that's one of the things that you can make with additive manufacturing. But there are sort of There's feedback between how you design your lattice structure in terms of the strut orientations or sizes and what the grains and therefore mechanical properties look like. And so that's one of the things that we're looking at, because this has implications for things like topology optimization. So that's just an overview of some of the various research topics. And I'm going to focus on, as I mentioned on the first slide, trying to link DFT-based predictions to at the atomic scale to macroscopic crystal plasticity models, where we want to be able to eventually understand and predict the engineering stress strain behavior of engineering materials. And we'll do that through this mesoscale link of defining our slip system behavior. So the motivation for this is that crystal plasticity finite element modeling is, it's a more detailed method than continuum plasticity modeling. This allows you to define the grains within your material and to understand how and to describe how the grains deform plastically. And so you get that information between grain level deformation and the macroscopic behavior of a polycrystal material. So you define your stress strain curve, but then locally you see how those grains deform. However, in the literature, there are many different hardening models and different approaches for defining crystal plasticity, but they typically have many different parameters which are eventually fit by fitting your computational model with a macroscopic stress strain curve. And so even if the hardening models are defined in terms of parameters that are meant to be physically significant, by that fitting process, you lose that physical relevance. And so first principles methods based on density functional theory, or DFT, we were anticipating and hoping could bring some physical meaning to crystal plasticity finite element parameters. And then if we could link these two together to try to say, let's bring some physical relevance to the parameters here, then we could use that to investigate materials with different properties. So different alloys, different grain sizes, temperatures, and deformation rates. So if we start off with DFT, what can we get from DFT-based calculations? So we can get the elastic constants, we can get the ideal shear strength, and then we can also apply, as we did in this, area, we apply strains to see their impact on how then the ideal shear strength or elastic constants change. And so this is pictured here, and if you have detailed questions on this, then Shunli's here to answer those. But basically, so how he did this is apply an alias shear where you have your system and you apply a shear on just the one layer, and then allow this to relax, and then measure and then compute then the ideal shear strength. And then okay, so that's going to be the ideal shear stress of that particular alloy composition or system. I should have mentioned, I guess, we're looking at pure nickel here. So that's a system that we're looking at, but again, we're hoping it's extensible to other things. So then if we want to think about then, so this just gives you then your ideal shear stress, but that's not thinking about plasticity and the fact that it's accommodated by dislocation motion. So we need to translate that to something that is more physically realistic. So we use the Peierls-Nabarro equation, which relates the lattice properties to the stress necessary to move a dislocation. So this is the original Peierls-Nabarro model, where we have our flow stress, or so this is the frictional stress for the dislocation to move through the lattice, and it's a function of the elastic parameters shown in blue, as well as Berger's vector and the dislocation width. And so what we chose to adopt was to convert our ideal shear strength to a frictional stress for dislocations, is this Dewsbury model, which adopts this parameter K, which is the anisotropic elastic factor. But what's important about K is that it depends on the type of dislocation. So the equation for K is given here, and this allows us to describe basically the resistance, the flow resistance for an edge dislocation or a screw dislocation, depending on this angle phi. And here is where we'd feed in then that ideal shear strength from the DFT-based calculations. And so what we wanted to do is say, okay, we can find then our ideal shear strength for our nickel, and say that we find our ideal shear strength for nickel, but then we want to say, okay, we can then calculate a parallel stress for an edge dislocation or a screw dislocation, but we also want to say, how does that ideal shear strength evolve if we apply some shear strain, which is going to relate to basically the elastic strain fields around dislocations, as well as when we think about dislocations interacting. Okay, so that's this part here. So the idea here is to say, we took a look at these and said, okay, if we have our close packed plane and our FCC single crystal, we applied a shear strain, or a pre-strain we called it, and this is again going to represent our elastic stress field, and then when we think about edge dislocations, and then we're going to talk about how that relates to sort of the edge, the dislocation interactions with larger strains. So we apply a pre-strain, and then we measure the ideal shear strength again as a function of the amount of pre-strain that we apply. And let me bring these up here. And so when we do this, then what we're looking for is our shear strength, which is now this is just a calculated edge Parles-Navarro stress based on the ideal shear strength that Shun-Li calculated, and as a function of applied shear strain. So we can see that the Parles-Navarro stress, now that we're calculating for an edge dislocation, increases with that applied shear strain to the system. And we also check to make sure that the initial critical resolve shear stress compared well to literature values. So this is from the DFT-based calculations, and then this is a plot of just saying these are critical resolve shear stresses as a function of year reported in literature, and showing how they scatter for pure nickel, where there's variations here in terms of how these values were obtained, as well as the purity of the nickel, which would impact those properties as well. So, but we're just comparing this 9.4 value to this range here, where the average is 11.7, and there's this range from 5 to 20. Okay, so yeah, so the ideal in resolved shear stress increase as a function of strain. So this is what we can get from our DFT-based calculation, this along with the elastic constants. And then we want to relate this figure on the left to say, okay, can we describe then how our crystal is, or how the particular slip system is strain hardening. So we need to adopt then a model that describes our slip system hardening rate. So what we adopted was this Piercesaro-Needleman hardening model, which was implemented in an Abacus UMAP by Huang, which is publicly available. And so this is the framework for crystal plasticity. So we define basically our shear strain rate on a slip system alpha, and it's a function of our current flow stress or of our slip system. So our current basically resistance to shear deformation on that slip system. So that's our tau C alpha. And we need an evolution law that describes how the strength of that slip system evolves. And so the Piercesaro-Needleman framework is basically these bottom two equations. So this is where I was saying earlier, there's many groups that adopt different frameworks for crystal plasticity, where you can have different hardening rules, where this is a function of things like dislocation densities and so forth. But then again, you can have quite a few parameters. And one of the reasons that we adopted this model is that it's able to capture the behavior that we're interested in, and it does so with very few parameters. So this H alpha beta term describes then the hardening rate on the different slip systems. If alpha equals beta, then this prefactor is 1, and if alpha is not equal beta, then this is 1.4. But the parameters that we have to calibrate or compute or predict somehow are H naught, tau S, and tau naught. So there's only 3 parameters in this model framework. And tau naught would be our initial critical resolve shear stress. Tau S is a saturation value, and H naught is related to the linear strain hardening at small strains. Okay, so if we now take a look at the DFT-based calculations, we had this plot of shear stress versus shear strain on a couple slides back. And so we take then for our parameters, so we're not calibrating at this point, we're just taking the values directly from DFT-based calculations, which are these 4 black symbols. We take our initial critical resolve shear stress as our tau naught, and then we take the slope of this at small strains as our H naught. And for tau S, we set this to 40 megapascal. So again, that's a saturation value. That's obviously not something we can get from DFT-based calculations. So we took a value from literature, but these two are coming directly from first principles. We assumed edge dislocations, which was from that previous Parles-Nabarro stress calculation, the lower, that's going to be our lower flow resistance. And then if we do this, what these plots all show are these are all engineering stress strain curves for different for 2 different studies in literature. So this is Hassan and Yao, and Hassan had done some tests on single crystal wire, and Yao had done some tests on this flat tensile specimen. Also for this is all nickel. And so what this is showing is the experimental data are shown as these symbols. And then the crystal plasticity finite element simulation is shown as these lines. So you can see that, okay, we can capture a little bit the behavior at the small strains, but once we get to large strains, we're not able to capture that, right? And so, so this is kind of signaling that this reliance on just edge dislocations and their contribution isn't enough to describe the full stress strain behavior of these materials. And I also should point out that these are for different directions as noted in the brackets. Okay. So the next step then is to say, well, let's look at our macro scale results and how do we account for large strain? So our thought process, I'll bring this up here, is that so as I mentioned before, we had this pre-strain, and that's basically accounting for the fact that we have elastic deformations in our lattice due to the presence of dislocations. And we calculated our piral stress for edge and screw, but we only so far looked at edge dislocations. And so we said, okay, if we look at this a little bit in more detail, when we know that for small strains, our edge dislocations are what's going to dominate, but when we have large strains, then we start having junctions between dislocations, and those junctions have screw character, which have this much higher flow resistance. So the schematic of what we did is we took, so from before I showed our tau versus gamma beta for just edge, but now we're saying that that's not enough to capture the strain hardening that we see on the actual experimental data. And we recognize that there should be some contribution of screw dislocations eventually. So we proposed this new method where we have incorporated this this weighting factor W, which allows us to then go between these 2 curves. So basically start off by saying, and this is the equation that's important here, start off by saying that when we have 0 strain, well, when we have very small strains, our edge dislocations dominate, but as we start to accumulate plastic strain, we have contributions from those screw dislocations. And we did calibrate this. So this is the one value that's calibrated, and this was calibrated from the Yao et al. Data. And then we go back, and so now these again are the black symbols then correspond to the, if we use this equation to find now our data points from the DFT-based calculations, we can fit now our new H naught, so the new slope that basically interpolates between our edge dislocations and screw dislocations, and we have the same tau naught. So we got this value of 0.33 for W by fitting this Yao et al. Data. But if we now compare to the Hassan data, so this was not used for fitting, we're able to capture the large strain behavior in these 2 different directions. So this means that by incorporating first the dependence on edge dislocations, we can get information about the small strain, but then to predict the large strain deformation of these materials, we need to account for the fact that screw dislocations play a role. So having these different sort of interactions at far field and near field. So in summary, at low strains, the main contribution is due to these long range dislocation interactions, which dominate, which means that elastic stress field around the dislocations. And then at high strains, the short range dislocation interactions dominate, which means the interactions or intersections between the edge dislocations forming the screw character. And so we use a DFT-based calculations to look at the atomic scale to understand basically that ideal shear strength. We then converted that to a Parles stress or a resistance stress for dislocation motion for both edge and screw, and then use that to inform a slip system model, so hardening behavior of a slip system, and then scale that up to finite element crystal plasticity, finite element analysis to check with experimental data. And so this is the similar approach that we're proposing here, basically integrating the DFT-based calculations with the crystal plasticity framework. So that's all I have for today.